Good day and welcome to Dubeke Consultz. Recently, we've been looking at the structural aspects of the telecom industry. With proper observations, you will agree with me that we have quite a number of channels that speaks about other structural industries, mostly our residential or commercial buildings, and at times our highways. But there are little or minimal channels that actually speaks about the telecom industry. And being one of the industry that I'm very experienced in, I have decided to take that responsibility of introducing the structural aspects from the scratch. So we'll be starting from the basics of the basics till we move to stages like the analysis and designs of this structure, and also move on to the construction aspects of this wonderful industry. With that being said, today we'll be looking at some of the key terminologies that you always get to encounter once you have dealings with telecom towers or our telecom marks. Starting off, I would like to remind us that these terminologies are not limited to what I have listed here. There will be subsequent classes that would be, taking care of further terminologies, or in case you have other terms that you want to get understanding of, you can as well drop them in the comment section and we'll make our time to make proper explanation of what those terminologies mean. So we'll be starting off with the member type. So I have listed some member types here. So these are mostly the common member types that you get to come across. And I would also like to put it in our mind that our member types for this design and construction are not limited to these three members only. Only that these are, I would say, they commonly used in our, let's say, 90% of the towers. This is what you mostly get to come across. So we have our angular lattice, we have the tubular sections, and we have the monopoles. Now, the monopoles and the tubular sections, they are most likely, I would say, they fall almost in the same category when you are talking about um, trying to choose them from the code. But we'll get to that along the way as time progresses. So let's start off with this angular lattice. So as the name implies, it forms something like somewhat like an angle at this point. This creates something like an angle. So it's mostly identified, or when you get to see their annotations, they always come in this format, or always come in this format. Now if you're trying to design them as well, you will mostly find them in this format in your softwares. You mostly find them in this format on your software, depending on the code you are using to design. So we have our EA and we have our L. So what EA represents is simply our equal angle. So when we have EA by 60 by 60 and by 6, so it simply means that this part to this part is 60. No, this is an equal angle. So it means this part to this part is our 60, while from this point to this point is our 60, and this to this place, which is our thickness, is our 6 mm. Same thing as this, just a different representation, as I said earlier, depends on the code you are using for design, or the code they are using to reference these annotations. This is, I've been able to call this thing out in this point, at this point, for them to be very simple to understand. And if you are someone that is familiar with steel designs and construction as well, you agree with me that there are some points in that you have to come and build these members by yourself. So for you to do that and do that adequately, you can always make reference to our design code of our engineering design code. So this is a simple steel table. So, and this is able to, so let's say we want to build a specific member ourselves that was not in the software, as we said. So let's look at 90 to This is also an equal angle, because if you look at this part, we have equal angles. This is equal angles. Don't forget that we also have unequal angles, right? We have some members that the length and the width are not the same, but in this case we are focusing more on the equal angle. So I want to build a member of 70 by 70 by 7. So this represents the thickness, while this is the length times the breadth, or h by h, because they are mostly the same thing. So I will have to impute my length and my width, then impute the thickness, and as you know, this is our mass per meter in kg. This is our mass per meter in kg. So for me to get that member correctly, I have to impute some of these other parameters, just like our torsional constant if the software is requesting for that, and maybe our elastic modulus. So they, as you observe, they are all different for each of these members. So in case you want to build your members yourself, maybe you did not find it in the design software, you can always come here and select the adequate properties. So moving on, we'll be looking at the tubular sections. So like I said earlier, our tubular sections and our monopoles are most likely in the same category. So why I had to separate them is because when we speak about monopoles, they are I would say they stand on a single leg, whereas the tubular towers, they could be three-legged, they could be four-legged, that are interconnected together, or depending on whichever case it is. But the monopoles has to deal with just one leg, but their identification, they come in the same format, meaning, as they are tubular sections, meaning they have a diameter and they also have a thickness, right? So you can also find that in our code. Maybe there's a particular member you want to build yourself, or that is the only member that is passing that design, and you need to fabricate that very member. So you can choose from our design code and also choose the adequate properties that follow suit. So we've spoken about our equal angles, our tubular. Now there is an addition here to our equal angles. We have D before the EA, then also to this L. This also forms an L. So it is also, so that is why this other code refers to it as L, because this forms an L angle, right? So there is also another addition to this L, which is our BB. So when we speak about BB, we are referring to back to back. So they are called back to back members, and this is our this is another way of identifying our back to back members. They are called this D in front of the DA is the double equal angle, and these are not strange, or these are not just formulated. You can also find this in the You can also find this in our design code. So depending on the member you are using, you can go there and select their properties and model them by yourself. So these are our equal angles that are back to back. So they are either back to back, or they are called our double equal angles, right? So let me show you an illustration of what we mean by our double equal angle or our back to back. So this is just a single angle, right? This is our angle ion that has just one singular members. And if you look at this other picture here, you will get to find out that these members are placed apart. Yes, so these members are placed back to back each other. One is a single angle. This is just an equal angle, right? This diagonal is just an equal angle. Why this angle is a double equal angle that are placed back to back. So still on this member type, these are simple examples of a tubular tower. So like I said, the difference between this and this right here is because this is just a singular member going straight up, and one thing is this is always larger and in size, right? That is for sure, due to its height and everything. Is always larger in size, while these are smaller. So this is our tubular towers. Our diagonals here are also tubular. Then this is our angular lattice, right? The legs and diagonals, horizontals, and everything, they are all equal angles. They are all equal angles or double equal angles. So these are our angular lattice, our monopole, and our tubular sections. So next key terminologies that you will always come across, this one is always, is our sections and our panels. Alright, so I've been able to make a little note here that our panels are subsegments of a tower sections. So panels are subsegments of the tower sections, while a sections refers to a segment of the tower. So let's not get ourselves confused, right? So this members, they are fabricated in parts. They are fabricated in parts, and like we said earlier in, or you can go back to our previous video, we said they are connected together by what? Our leg splices. So these members, you cannot just use one members straight up to the apex of, you cannot use one member straight up from the first section to the apex of the tower. You know, the slenderness ratio and a lot of factors that will be involved in that very scenario. So they have to be subdivided into different sections. Now this section, this is an example of what a section looks like. Now these sections can also be subdivided into different panels. As you can see here, this is a full section, while this part we have a first panel here, and we also have our second panel here. Now now when you get into the design, or when we get into the design of these members, you will get to find out that at this particular section, right, this diagonal might be failing, and why this diagonal might be passing. And let's not forget that our section can also consist of just one panel. So it does not mean for it to be called a section, it has to consist more than one panel. So our section can also consist of just one panel. It can also consist up to 3, 4, 5 different panels. It just depends on the general, or it all depends on the general arrangement of that very tower. So our face width, how to properly measure our face width for our tubular members. It is the distance between the tower legs taken from the center to the center. So when we are dealing with tubular sections, the face width of those tubular sections are taken from the center of one leg to the center of another leg. Whereas for our angular lattice, if you are talking about the face width, it has to be taken from the edge to the edge. So we can have the face width of a section, and we can also have the face width of the tower itself. So for the tower itself, it means this accurate measurement at the base and also at the apex. So let me show you this illustration. So let's say we want to connect these members together, and we want to use our previously mentioned angle iron, which is 60 by 60 by 6 mm. So imagine what 6 mm looks like. You know, it is quite tiny. So if you want to connect these members together, it will be very difficult for you to connect these members at the center to the center, which is the center of those 3 mm. So let's say this member below rather is 6 mm thick, and this member above it is 5 mm thick. You know, trying to connect those two members together, it will be really tough. I don't think it is actually possible. So this angular lattice are connected at the edges. As you can see here, they are connected at these corners, right? So the face width has to be taken of that very section of that very tower, has to be taken from this edge to, you know, the other edge. But when we get to the tubular towers, you will find out that it will be very difficult to align this because the black line here represents the top section, while the red ones here represent the below section. So we have diameter 200. They have a tubular section of 200 mm diameter, and another one of, let's say, 150, right? So it will be difficult to connect this at the edge of this point, but they can be connected at the center. Then the flanges can now take care of these excesses at this point. They have to be taken from the center of this point to the center of another leg. So this is how to properly mention, or how to properly measure the face width of a tower, or when they represent a face width, they give you a face width at 6 meter for a tubular section. You should understand where they are taking that very measurement from. So now let's talk about the braces. So if you are familiar to engineering, you agree with me that you always have to brace your steel sections, for rigidity, for it to be more stable and the rest. So there are various ways in which we can brace our tower members. So I will always keep referring to some of our previous videos, because that is the reason why we make numerous videos, so that what we cannot cover in this very one, we show you where you can get to understand them in maybe the previous videos made, or so in our previous videos you get to understand that this represents our diagonal members, while this represents our horizontal members. So there are different ways in which we can brace these members. So we have the X brace, which is one of the most common type of bracing you will always come across, and simply because this forms what's like an X at this very point. Now we also have our K bracing, just like the name implies, it also forms a K. This forms a K, while this forms a mirrored K. Then we have our V bracing. We have our V bracing. So when you see a tower section, you will be able to identify the bracings that are used for either that section or the panels, because there are some sections that you can have X at some point and you can have K at another point. It all depends on the designer or the reason behind that very design. So we have our V bracing, then we have our inverted V. So this is our inverted V. So it is our V bracing, but it is just that it is flipped to the other side. It is flipped upward. Then we have our Z bracing. So our Z bracing are sometimes referred to as our diagonal bracing. So if you get to come across diagonal bracing, just diagonal bracing, or then you should understand that we are talking about our Z bracing, because this forms a Z at this point, or this can just be called a diagonal brace. So moving on from bracing, we'll looking at our tower slope. So when we are talking about tower slope, because when you are making designs on this structure, the softwares can ask you how many slope does the tower have, and from what point to what point is the tower sloping. So this is a two slope, because from this point to this point we have a different angle of inclination. These are inclined inward. So we have the first slope ending at this point, and we have the second slope going to this point. So it depends on the tower. You can sometimes have more than two slope on that tower, while for this case it is just a singular slope, because it is just one member that is aligned and going straight up. There are no change in the angle of inclination. So we'll finalize sloping at this part, and we'll move to our support type. So when we talk about the ground-based tower, it means we are telling the software that this tower, it solely depends on the base, which is the foundation. There's a foundation, just like every structural. There's like every structures, there is a superstructure and there's a substructure. So below this, there is a foundation here, as we all know. So it means that this tower solely depends on this foundation, solely depends on the foundation below it. Whereas we can also have our guide towers. So it doesn't just depend on the foundation, it also depends on these anchors. These anchors, they also provide help in making sure and the stability of this very tower, and these anchors are anchored to this guide base. So if you want to know more about this guide base and the reason behind some of the design of these guide towers, you can check our previous videos as well. They've been carefully explained why there is need to guide our tower. So it can also, so that means, so to say, our towers can be ground based, it can be guide. So it is not limited to these two types of support only. We can also have towers, just like our rooftops, we can also have towers that are supported on our plate girders or our I section H beams. Depends on the how you choose to identify them. Those are other types of support that we have, but these are the most common that you will always get to come across, mostly our ground-based towers. So another key thing you will always come in contact with are our stiffeners. So this is what a stiffener look like. There's a stiffener here at this edge, and there's a stiffener here also at this point. So these stiffeners are used, to simplify it, I would say they are used to keep our members in check. This is our main leg here, as we've explained in our previous video, why these are our stiffeners. So this is used at the end of this tower legs to ensure that it does not have any reason to move to this point or to this point. So it's used to stiffen these members. It can be applicable on tubular sections, on monopoles, b-boards, and different steel sections. So this is also a stiffener inside. This is looking at the outside, while this one is looking at the inside of another tower. So it is also used to stiffen, to keep in check these members at their appropriate position. This is just to simplify it in a very common term. So going forward, and probably the last for this lecture, we'll be looking at our base plate and probably our anchor bolts. So our base plate, this is what our base plate looks like. So this base plate is a thick section, mostly thicker than our angle iron. So it has direct contact with our grafting, or it has direct contact with the concrete part of this structure and the steel part of this structure. We cannot just put our tower legs on the concrete directly or on this grafting directly. There has to be a plate connection. These are called anchor bolts, or they are called the hold down bolts, and they function differently from our normal bolts. Why these bolts are used for the connection of members together, maybe diagonals and horizontals and the rest. These anchor bolts are used to connect the steel part of this very tower to the concrete part of this very tower, and they are always inserted deep into the concrete, because this is the bolt that is holding the entire tower itself. This bolt you see here, they are what is holding this entire tower to this very concrete structure. So they have a bigger diameter, and they have a very long let me see, they go deep down into the concrete, more than what your eyes can see at this very point. So to finalize this lecture, I have brought out the base, what the base of a tower looks like. We call it the stop base, and it consists of some of these key terminologies that we've spoken about, just like our as we said, this is our base plate, this is our grouting. We'll get to look at grouting in details and how to properly do them later. This is our base plate, this is our hold down bolt or our anchor bolt, which we said goes deep down into our concrete. This is our stiffener, used to stiffen these members at this point. This is our tower leg, or our main leg. This is our bolt holes. There has to be holes in this member for us to be able to connect each of the tower sections together. So these are our bolt holes, while this is our diagonal, and this is our gusset, as explained in our previous classes. So these are the key terminologies that you get to come across, and in case you have any terms that you've seen when you've been working, or you came across some tower drawings or some detailings and the rest, and you feel the need for them to be captured in this video, we might have omitted them in this very class, so you can do well to drop those terminologies in the comment section, and we'll be able to have a look at them and create time to make sure that we create more videos that we carefully explain what those terminologies represent. So please do not forget to like and subscribe to our channel, so more videos will be coming our way introducing this very industry, how to design them, how to construct them, and the rest. So please kindly subscribe to our channel. Once again, thank you for staying with us at Dubeke Consultz till this point in time. We really appreciate your patience. Please subscribe and like our video. Thank you.